Lesson 323, Part 2, and an introduction to Lesson 324. So going back to the graphs that we made in 323, we now want to look at how we can use sigma notation to express the sum that we used to approximate the area under the curve. So think back to the problem for the last lesson where we graphed the curve x squared, and we were trying to find the area under that curve between the intervals of 1 and 3. And we're going to write our subscript values underneath that graph. So we have x sub 0, x sub 1, x sub 2, x sub 3, and x sub 4. So if I want to write a linear equation for x sub k, x sub 0 started at 1, and I'm adding 0.5 every time to get to the next increment in my rectangle. So my linear equation is going to be 1 plus 0.5k, because each rectangle had a width of 1/2. Now if I want to write an expression for the heights of each left endpoint, so how am I calculating that height? Remember, I'm plugging in x into that function. So if I want to find the height using x sub k, I'm going to square that. So substituting for x sub k, I'm going to have 1 plus 0.5k squared, because the width of each rectangle is 0.5 units. So the area of the rectangle is the height times the width. So I can use my expressions that I just made to write an equation for the area of left endpoint rectangles in terms of k. So if the area is equal to the height times the width, the height of each rectangle is 1 plus 0.5k squared, and the width of each rectangle is 0.5. So that's an equation to approximate the area of a left endpoint rectangle. Now if I want to find the sum of the areas of the left endpoint rectangles, I can add up the area of each rectangle, and I can write that in sigma notation with k starting at 0 and going to 3. Because remember, when I labeled my left endpoints, I started with x sub 0, x sub 1, x sub 2, x sub 3. So I'm calculating that interval 0 to 3. And my area is the height of each rectangle times the width of each rectangle. Now if I wanted to change this up and use right endpoint rectangles instead, I can label my intervals. So x sub 0, x sub 1, x sub 2, x sub 3, x sub 4. But now look at where my curve hits my right endpoint on my rectangle. At x sub 1, at x sub 2, at x sub 3, and at x sub 4. So now if I'm going to write it in sigma notation, my k values start at 1 and go to 4. My height is the same, and the width is still 0.5. Then in the problems from yesterday, we calculated the area under the curve using smaller intervals of rectangles. So if I want to write sigma notation for left endpoint rectangles, I've got x sub 0, x sub 1, x sub 2, x sub 3, and so on, up to x sub 7. So my left endpoints are at 0, 1, 2, 3, 4, 5, 6, 7. So k is going to go from 0 to 7. And finding the area of each rectangle, my width is now 0.25. And my height is 0.25k plus 1 squared times the width of 0.25. For right endpoint rectangles, I would be shifting these over a bit. So now my k is going to start at 1 and end at 8 with the same height and the same width of each rectangle. Moving on to section 324. We can use area under a curve to solve many different problems. And you're going to encounter area under the curve in a tremendous amount of calculus problems. So in this example, we are describing population. So we're modeling the rate of population using that equation. So sketching a graph of 2 to the x power and finding the area under that curve between the interval 2 to 4. And we're putting 5 rectangles underneath that curve. So if we think about labeling this graph and think about the points on this graph, when x is 2, remember your input and output in your table. When x is 2, y is 4. So you've got the point 2, 4. if I find the width of each of these rectangles, I have the distance between 2 and 4. And I want 5 rectangles. So each rectangle has a width of 0.4. So if I want to calculate my next left rectangle endpoint, I'm going to put in a 2.4. And I get out 2 raised to the 2.4 power. And then I'm going to put in a 2.8. And I'm going to get out 2 raised to the 2.8 power. And then put in a 3.2 and get out a 2 raised to the 3.2 power. And then put in a 3.6 and get out 2 raised to the 3.6 power. So these values on the graph, x sub 0 starts at 2, x sub 1 is at 2.4, 2.8, 3.2, 3.6, and 4. So looking at part D, why can a left endpoint rectangle approximation of the area under this curve be expressed as this sum? So looking at the sum of those rectangles, remember that the area of a rectangle is equal to the width times the height. So if I want the sum of the 5 rectangles, I have the width times the height of that rectangle plus the width times the height of the second rectangle plus the width times the height of the third rectangle, fourth rectangle, and the fifth rectangle. So factoring out the 0.4, the sum is equal to 0.4 times the sum of each height. So if I want to express this in sigma notation, I'm going from 0 to 4. And I have the width of each rectangle. And the height is expressed as 2 raised to the 0.4k power plus 2. I'm starting with 2, and I'm adding 0.4 times k every time. So if I want to use left endpoint rectangles to approximate this area, I can use that sigma notation, plugging that into Desmos or plugging that into my calculator using the math 0 function. I get approximately 15.023. And since we're modeling population growth, that's telling me the population grew by 15 people in the last 2 years. Is this an underestimate or an overestimate? Well, we had an increasing function and we used left endpoint rectangles. So we have all this space that we haven't found the area of. So that tells me that I have an underestimate of the actual area. Because left endpoint rectangles give us an underestimate in an increasing function. Look back at your math notes for this section. Remember, left endpoint rectangles touch the curve on the left side of the rectangle, and right endpoint rectangles touch the curve on the right side of the rectangle. And using sigma notation, left endpoint rectangles will start at x sub 0, whereas right endpoint rectangles start at x sub 1. Homework for this section are problems 134 through 138. And that wraps up chapter 3. We'll begin to review and test on this next week. Have a good night.